Good morning and welcome to the first day of the American Gem Trade Association's Dynamics Seminar Series. Our next speaker, Dr. Thomas Hainschwang, is director and co-founder of GGTL Laboratories. He founded GemLab Liechtenstein in 1996 and joined a very close collaboration with GemTech Lab in Geneva in 2011, through which GGTL Laboratories emerged, with the 3-member labs in Liechtenstein, Geneva, and Antwerp. Dr. Hainschwang has been working on the analysis of diamonds, colored stones, and pearls for the last 29 years. He is a respected expert in the field of gemological research with extensive experience in the complex topic of fancy colored diamonds. Besides his expertise as a multidisciplinary gemologist with specialization in diamond research and testing, Dr. Hainschwang has developed and built many analytic instruments for gem and pearl testing. Dr. Hainschwang holds a PhD in physics in material science from the University of Nantes, a university diploma in advanced gemology from the University of Nantes, the DUG diploma, and not surprisingly, he has his GG from GIA, an FGA from the British Gemological Association, and his SGG from the Swiss Gemological Society. Please join me in welcoming Dr. Thomas Hainschwang.
Okay, good morning, everybody. It's a pleasure to be here, and thanks for the invitation to AGTA. I'm going to be talking about fluorescence. So everybody of you knows fluorescence in diamond and fluorescence in colored stones. To many in the trade, fluorescence is not much more than a nuisance for pricing colorless diamonds. So the more you have of it, the lower the price is going to be. But there's much more to it. So I'm going to be talking about the pretty images today, but also about the applications in diamond testing that we use fluorescence for, which is much more vast than most of you could possibly even imagine. So let's get into it. What is fluorescence and phosphorescence, the two terminologies that we hear in gemology all the time? So fluorescence is basically an effect when you're, let's go stick to diamond. When you have diamond, the diamond absorbs light. The electrons in your diamond are going to raise to an elevated, so-called excited state from the ground state. And this state is not stable. So this energy needs to be lost somehow. And this loss happens by 2 or 3 processes, 2 most likely. So one of them is emission of light, which is fluorescence, and the other one is just vibrations, which is basically loss of heat through vibrations. So that's how a material can lose this energy that it acquired by absorbing light. Okay, so that's the basic description of what is fluorescence. Fluorescence itself is a fast process, so it happens in milliseconds. So when you turn off your UV source, the fluorescence effect will stop immediately. And then you have delayed fluorescence, which is also known as phosphorescence. Here, the time of delay that when you turn your light source off will be anything between 10 to minus 5 seconds, I think, to several hours. So you can have chameleon diamonds that phosphoresce still after an hour when you're in absolute darkness. So that's what phosphorescence is. What do we use to check fluorescence? Normally, traditionally, most gemologists use this kind of a device. So it's just a regular long-wave, short-wave lamp, small device, not very expensive. Emits UV at 365 and 254 nanometers, so it's long wave and short wave UV. To make it clear here, fluorescence can be excited by any wavelength of light as long as the defect responsible for that fluorescence is found at a longer wavelength than the excitation light source. Means if you want to excite the N3 center, so the blue fluorescence in a Cape diamond, you need a light source that has a shorter wavelength than 415 nanometers. Okay, so if you take a laser at 473, it will not excite the N3 center. It needs to be a shorter wavelength. So The most practical sources for gemology are obviously UV sources, since first of all, they don't interfere with the luminescence that you see by your eye, and second of all, they're readily available. In gemology, we use anything. We use anything from the deep UV all the way to the near infrared to excite fluorescence, but that's for a later slide. So let's go on. So in fluorescence, a really big step was made in the late 1980s, early 1990s, when De Beers started to make images with their diamond view unit, which is a fluorescence system that doesn't excite under the classical UV excitations 254 or 365, but in the deep UV. So here we are exciting the fluorescence with an excitation at 225 nanometers, which correlates to the energy of the band gap in diamonds. So the energy is basically at the limit where pure diamond absorbs light. So pure diamond absorbs light at exactly 225 nanometers, or just below. Okay, the rest of it is transparent. So by using this kind of a light source, you're making it possible to see surface-related fluorescence much more easily and readily than with any other UV source. That's why they started using this excitation exactly at the band gap energy. And with this device, this was actually built mainly for the detection of synthetic diamonds, because in those diamonds you can visualize the patterns much better at deep UV excitation than any other UV excitation. At least that's true for colorless synthetics and for blue synthetics. And that was a really big step. Now, in a laboratory setting, you don't want to just visually excite the fluorescence, but you also want to know what the fluorescence is caused by, and that's what we use spectroscopy for. So basically, we're exciting the fluorescence, and we measure with a spectrometer at which wavelength this band is emitting and what structure it has. And through this information, we can often identify what defect it is, and it gives us lots of information about treatments, authenticity, etc. In a regular lab setting, the most typical thing you want to find for fluorescence measurements are Raman spectrometers. Raman spectroscopy is not the same as fluorescence spectroscopy, but since these systems use lasers that excite also fluorescence in your gemstone, these are basically misused for fluorescence spectroscopy besides their other application, which is Raman spectroscopy. There are two different techniques. I'm not going to get into the differences between the two, but we're looking at fluorescence and not Raman effects here. Okay. This is a system in our lab that I actually built myself. So we're currently using 7 laser excitations from the UV to the near infrared. The importance of all these excitations, I'll show it a little later on just also the imaging, is that the various defects in diamonds that fluoresce do not always show up with the same laser. So you can't just use one laser and think you're going to see everything, but you have to have a big range of lasers available, and you have surprises every time on every diamond. So you basically, it forces you to use a range of excitations. In about 2009, we started to combine fluorescence and imaging and spectroscopy in one system. And that's actually the system we use for, all the images that you're going to see in here. So all the images seen here have been recorded on this system here. This is the DFI. This is like the biggest one we have. This is a very high power xenon source that has been suitably filtered to enable us to excite a diamond with any wavelength in the UV. So anywhere from 210 to 400 nanometers we can excite. And we enclosed a laser here and a laser in the back, so we can also excite at 405 and 532 nanometers for both fluorescence imaging, fluorescence spectroscopy, and also Raman spectroscopy, so we can do all in one. And here we have a spectrometer, here is the microscope, camera, so we do the imaging and the spectroscopy all at the same time. And these systems here, we actually developed them specifically for melee diamond testing, but it extends way more than that nowadays. We test everything with it. but the main applications are for melee testing because it's very efficient and very rapid. To give you an idea of why we built this, this is the same diamond here. Same acquisition time on both sides. This is with a standard 365 nanometer lamp, and this is on our DFI. So we measured the output, and we're at 350 times the UV output than a regular UV lamp. So the goal was to have a system that enables you to make anything fluoresce. So if you have a diamond that has a report that says no fluorescence, I can guarantee you it will fluoresce between medium and strong under this system. So that was the point. The point was things that don't fluoresce, we need to see what defects are in them visually already. So now, what's the point? Why do we need so many excitations? So why do I not only work with deep UV? So why doesn't the diamond view alone does it all? This is an example that we had recently at the lab. So this is a typical Zimbabwean stone with a beautiful phantom in the middle. This phantom shows that the diamond is predominantly of cuboid growth. So cuboid growth being not cube. I always have to distinguish those two. Synthetics have cube faces. Cube faces are flat-faced cube faces. These are cuboid. So cuboid are undulating faces. They're rounded. They're never flat. In diamond, those cube faces that we see in synthetics actually do not exist. So this is a cuboid diamond, mostly cuboid with a little bit of octahedral sectors as well. Let's have a look at it. So if you have only a diamond view at hand, this is what you're going to see. So you see the whole thing is surface fluorescence, is pretty opaque, and you have those transparent window where this diamond is transparent, 225 nanometer excitation. This is 220, not very spectacular. Now let's look at the stone at long wave UV, basically. So we're seeing almost the same. Still not very spectacular. And now let's go into shortwave, and there we are. So you're seeing all the growth that becomes visible that before was invisible at 260 nanometers. There it is. And depending on what diamond you're testing, one excitation may be way better than the other, and you can't always predict which one it will be. That's why we have developed this system where we can, by joystick, switch wavelength in milliseconds. So let's go into the practical applications. Let's go into the distinction of natural diamond from synthetics. And let's have a look at some images of natural diamonds under fluorescence. So this is a first image of a stone that's rather exceptional. So this is a very large 10 carat plus brownish pink diamond with strong orange fluorescence. Here you see these little patterns here are all dislocation networks. It's a type 2A diamond. And this has this beautiful orange fluorescence. This is very rare. You don't see that very often. You see these dislocation networks. You know this stone is natural and of natural color even. Let's look at the most common ones. The most common ones, Cape series diamonds. So if you have a Cape diamond, just a D to Z regular Cape diamond, this is a typical kind of reaction you will see under deep UV. So this is deep UV excitation. What we're seeing here are cuboid and octahedral growth sectors. Cuboid growth is common in diamond. It's more common in some than in others. In Cape stones, it's not very, very common. You often see some small sectors that are of cuboid growth. It's much more common in vivid yellow type 1B material. There you see lots of cuboid growth. And you can visualize it with deep UV excitation really only. If you look at this stone on the long wave, it's just going to be plain blue, so it won't be very, very interesting to see. This gives you much more insight into the growth of the diamond. Two more examples of Cape stones. Here you see these interesting, you would say they look cube, but actually what you're seeing here are octahedral faces. Okay, this is just the other direction. So this is along the cube direction, and you see the octahedral directions being represented as if it was a cube face, but it's not. These are octahedron. Okay, so this is another way to see these goods. And let's look at type 2A diamond. Type 2A diamond is very different from type 1A material. In type 2A diamonds, we see commonly these so-called dislocation networks. So this is relatively high magnification. This is probably about 2 millimeters in a natural diamond. You see these spider web-like features in a colored fluorescing matrix. This is very typical for natural type 2A. You don't see this exactly as like that in synthetics. Some synthetics may show, let's say, similar features, but they are distinct from the typical dislocation networks we see in natural type 2A diamond. They happen because, curiously, the less nitrogen you have in a diamond, the more easily it is deformed, plastically deformed. So you get all those dislocations in huge numbers, much more so than in nitrogen-rich diamonds. Two more examples. On the left, a blue fluorescing one with dislocation network. On the right side, excuse me, on the right side, one with red fluorescence from the NV center. So those are also dislocation networks. They can occur in practically any color, these images. They're all deep UV excited as well. So here again, deep UV does the best job because type 2A diamond is transparent all the way to 225 nanometers. Here, a look at a couple of fancy color diamonds. So these are all yellows, and then there's a brown in there. So you see what gives us these spectacular images are the individual growth sectors. So these are all have alternating growth here. This stone here is a cuboid octahedral stone. You can see these beautiful patterns. It's a yellow mixed growth diamond. Here as well, we have the cuboid core. The rest is octahedral. This one is just octahedral, but with funny growth sectors. Sometimes very hard to explain exactly what happens during diamond growth looking at those images, but generally it gives you a good idea about what's going on, and for sure it gives you an idea whether the stone is natural or synthetic. Here, a yellow-orange type 1B. You can see the straight layers going in one direction here. That's from plastic deformation. So this stone had some plastic deformation post-growth, and that causes these dislocations along the octahedral direction and accumulations of H3 centers, which give you this green fluorescence. This little friend here, if you don't have experience, you would say, oh, this is synthetic for sure. It's not. This is a hydrogen-rich yellow diamond that's actually shortwave excitation. So they have spectacular growth sectors. You will see similar things in synthetics in a moment. This one, pretty well known. Rhodesian star, over 10 carats. In my opinion, still the best stone of this kind in the market. The pattern is absolutely stunning. So what you see here is the shape of the diamond itself is octahedral, as you can see. But these sectors that fluoresce green are cuboid. And you can tell here at the corner, and you can't really see here. Oh, here you see better. You see the cube here? Okay, this is slightly undulated cube. This is a cube face that grows from here to there. So all these sectors here correspond to the cube face of the cuboid face of the diamond. So this again is a mixed cuboid octahedral diamond. The cuboid sectors, they accumulate different defects than the octahedral sectors. That's why the cuboid sectors fluoresce green. That's from a nickel-nitrogen defect. That's why they fluoresce green. And the rest of these stones is generally inert. When you look at most of the material in the market, you'll see that they're generally inert. You have just the green sectors. The rest of the stone doesn't fluoresce. Here, we're in the lucky situation that the stone actually fluoresced this beautiful orangey, pinkish, kind of reddish color, which is just a modification of the N3 center with an additional band in the red that causes this interesting fluorescence. And this gives us this beautiful contrast between the two colors. So these stones, whenever you see, if you want to have fun with fluorescence, you buy some Zimbabwean material. That stuff is always rather spectacular under fluorescence. This is the type 1B. It's actually just a single nitrogen containing yellow, vivid yellow diamond. This is one of the most common kind of patterns that we see. But rarely is it so nicely developed that, you see this beautiful kind of Mercedes star pattern as we see it here. This is the same defect that causes this green fluorescence as what we've seen in the Zimbabwean stone before. Same thing. And here it develops these beautiful sectors again from mixed growth. So the growth again here is cuboid octahedral. That's why we see these features. And these features, they're especially this development of these reentrant faces here. And that's because most of those crystals, when you see a crystal of this material, oftentimes they don't form regular octahedra. They form stones that they look like hopper crystals. If you know how salt looks like when it crystallizes, they look like hopper crystals of salt. But it's not a hopper growth. It's just a mixed growth with reentrant faces. So you have certain faces that grow faster than the edges, and that gives you this interesting appearance of these stones and gives you this interesting fluorescence as well. Here a spectacular example of, again, a mixed growth diamond, yellow again, with this beautiful phantom in the middle. You would think that under a regular microscope you would probably see a beautiful phantom cloud right there, but actually you don't. In the vast majority of these samples, there is nothing. So you look at this stone under regular light, there's just nothing there. And you take UV, and there it is. It shows you its growth. It doesn't always do it under optical microscope, but just under fluorescence. This is a fun stone. So here, this is a tiny stone. This is like 1.2 millimeters. And it's something red fluorescing in the middle. Can anybody guess what that could be? What fluoresces typically red in the mineral kingdom? Corundum. So this is one of the rare diamonds that contain a corundum inclusion. I think there were actually maybe 2 or 3 of them in it, not just one. But I hit one of them was reflecting throughout the stone, this one here. So this one was exactly at the culet, so it was already reflecting on all the stone. What did I do? Focused laser beam, hit the inclusion, and there you have it, glowing all throughout the stone. So this is a corundum inclusion in a colorless natural diamond. So just to give you an idea, the most common defect when we look at these stones, the one thing that most systems that do currently automatic testing look for is this, okay? So when we do fluorescence imaging and at the same time we quickly look at the spectrum, or our system looks at the spectrum, it looks for this center here. If you have a distinct N3 center in a colorless diamond, or in the colorless to near colorless diamond, you know it is still of natural origin. There are some synthetics that do contain some of this center, but it's generally weak, or generally only, or when it's stronger, it's only localized in certain sectors. I'm talking about colorless diamond here. If we talk about yellow diamonds, this criterion does not hold, because they treat them, they create N3 centers. You can have strong N3 centers in synthetic yellow diamond, but not in colorless. In colorless, it has been described. Generally, what I have seen, they're localized only in lamellae within your stone, never throughout the stone. And I still haven't seen a stone that fluoresces strong. So I can even tell you right here, before we even get to the segment of synthetic diamonds, if you have a diamond that fluoresces distinctly any color, doesn't matter what color, under long wave, it fluoresces distinctly. So far, at this time, you can be almost 100% sure that your stone is natural. Because synthetic diamonds, when they are excited at long wave, no matter if CVD or HPHT, they never fluoresce strong when they're colorless. Again, limited to colorless, not colored diamonds. But for colored diamonds, that's a good clue. If you have a strong blue fluorescing stone, oh, you're fine. You don't even have to go and test it, at least until at this time. So let's have a look at the synthetic diamonds and how they look like. So in synthetic diamonds, you have this. We have these growth sectors. We have growth sectors just like in natural diamonds, but they are usually much more geometric. So you have these straight lines that separate octahedral from cube and other faces, but the most common is the cube face and the octahedron in the HPHT synthetics. So you always see these things. To visualize this, unfortunately, you do need deep UV. this doesn't visualize well on the short wave. You can see it down here in this sample. So here we are at long wave. Most HPHT synthetics at long wave UV don't do anything. They're usually inert, generally speaking. And the shorter you go, the more they fluoresce. So at 254, you do see it, and you do see also a sector in here, but it's generally much less distinct than when you go to deep UV, where you see this. What these things also do, they phosphoresce long-lasting. That's nothing new. It has been published on many occasions. Most don't know why, but it's actually because of boron. So these stones almost always contain a mini trace of boron. This is the reason why they phosphoresce long-lasting. Not to be, well, it's not, when you see this kind of a fluorescence and a long-lasting phosphorescence, it's not proof that your stone's synthetic. If you see these kind of sectors, then you know it's synthetic. But if you do not know if it's synthetic or natural. Because you can have natural diamonds, natural colorless diamonds that contain a mini trace of boron. They will react just like that. So they will fluoresce the same way. They will phosphoresce the same way. They will give either undeterminable or synthetic with your tester, because they will react exactly the same way as HPHT synthetics. Here are a couple of yellows. Yellows to blues. Yellow, blue, no, this is actually a pink because it's been treated, but these are yellows, yellows, yellows. This is a bicolor blue colorless, and this has been yellow, and it's been treated by irradiation and annealing. So that's the kind of patterns you can see. You see already from this image, it's more diverse than what we see in colorless synthetic diamonds. It's even much more diverse than that, because these are the characteristic features that you see. But unfortunately, there's plenty of those stones that don't show those characteristic features. So it's much more complicated than colorless synthetics. It's like one of the most challenging tasks of the lab to screen for HPHT synthetic yellows, especially when they're in really small sizes. When you get 10,000 stones and you need to know, are they natural, are they synthetic? It's really challenging because they have extremely variable properties that overlap quite a lot with natural stones, and they don't behave the same way. So it's not like HPHT synthetics in colorless, where you know deep UV, they fluoresce like that, and they phosphoresce. These things may fluoresce or not under any excitation, and they may phosphoresce or not under any excitation. And they may or may not show these features, so it's much, much more challenging to identify them. In identification of those stones of HPHT synthetics, spectroscopy plays some role, but honestly not very much. What you see here is the classical thing when you have a nickel-rich HPHT synthetic that shows these nickel peaks in photoluminescence spectroscopy. This is Raman, this is the nickel peak here at room temperature. And this is the nickel peak at low temperature. And this is the nickel peak that shows up only at low temperature at 4.8. This is like a quadruplet here at 484 nanometers. So this is kind of the typical thing that you see sometimes. But in the more recent productions, I've seen that I would say 95% of synthetic colorless diamonds don't show anything anymore. So if you go for spectroscopy, you're just going to have a flat line. And that by itself is very suspicious. So if you have a stone that at PL spectroscopy, low temperature, shows nothing, you're like, meh, that smells like a synthetic. Because in natural diamonds, you do generally find defects that are detectable at low temperature spectroscopy. Let's have a look at some CVD synthetics. So CVD synthetics compared to HPHT, completely different process of growth. So this is a layer by layer growth on a seed crystal, and you can see the layer by layer growth here, okay? You see the layers, you see them here as well. This is long wave UV for the same stone, and this is 405 laser for the same stone. So these stones typically show two defects when they're as grown. That's quite distinct. One is the NV center. The NV center emits in the orange, so that's it. The NV center is well excited with long wave UV, but not very well with 405 laser. So depending on what you use, your stone's going to be either orange or green. At 405, you're exciting the 467 nanometer defect, which is very characteristic for as-grown CVD diamonds. But generally speaking, you take a UV lamp, you have an as-grown CVD synthetic, it will fluoresce orange to red. Orange to red fluorescence in natural colorless diamond is very uncommon, so just put it aside. It's almost guaranteed synthetic. HPHT-treated synthetics, I mention it separately because it's a very common thing in the market. Much of the CVD material is grown very fast, therefore is very defective, therefore is brownish. So this brownish color has a similar origin like in natural diamonds. The brown color, you can get rid of it by HPHT treatment. And the HPHT treatment of CVD diamonds makes them colorless and completely changes their fluorescence properties. So this is an HPHT-treated stone under deep UV excitation. You can see this yellowish green fluorescence, and you see the growth lamellae just like in the other example. This is a deep UV image. Now, if you look at a stone that we treated before, this was before treatment, this was after treatment, at different excitations. Before treatment, as I said, it fluoresces orange. After treatment, it fluoresces rather bluish under the longer wavelength, and it goes towards green under the shorter wavelength. So this is very typical for CVD material after HPHT treatment. And here, an example that shows you how wide it can vary. So here we're at long wave excitation, and here we're at deep UV. So long wave, you can see, I mean, this stone fluoresces blue. So anybody tells you, oh, blue fluorescence doesn't exist for synthetics, it absolutely does. But, as I mentioned before, this fluorescence that you see here, if you take a regular long-wave UV lamp, it'll probably show as inert or faint, very faint blue. Okay, this is under a DFI, so it's high-power UV. That's why it's visible. But otherwise, it will be a very faint fluorescence. But anyways, you can be anywhere from blue through violet, through purple, through greenish blue, in long wave, in HPHT treated material, and every time when you go towards short wave and deep UV, you get into more of a yellow to green to orange response, which is unlike anything you would see in a natural diamond. And that's how you can distinguish them easily. You see a blue fluorescing stone, and it fluoresces yellow or green under deep UV, there's something wrong. A natural diamond would fluoresce blue down here. So the sequence would be blue, blue, yellow, yellow, blue, blue. Okay? So these sequences, that's what we use at the lab to distinguish them visually. We don't even have to take a spectrum. You usually do at the end, but you know, you see that and you know, oh, that's a CVD. The luminescence, as I just mentioned it, from an as-grown stone, I mentioned before, the red fluorescence is from the NV center, that's here. So here in the orange to red domain, the NV0 center, this is what causes the fluorescence that you see here. And the yellow fluorescence that we saw before, that's included here, is from the 467 center. So this combination is very typical. And this thing here, the silicon center, is very typical as well. So if you have a spectrometer on hand, even small spectrometers will visualize that stuff in most of the CVDs. Sometimes this is a room temperature spectrum, but it often works at room temperature. Oftentimes you don't have to cool down a diamond to see if it's a CVD or not. CVD is kind of a nice material to analyze by spectroscopy because it always gives you a result. HPHT doesn't. Now, if you have a doubt between a blue fluorescing and a blue fluorescing diamond, you see a blue fluorescing diamond, and you're like, oh, it fluoresces blue, it's natural. These are the two responses of natural diamond versus synthetic. So you can see that this band in the red here is centered in the blue. That's why you have blue fluorescence. The blue spectrum is from a natural diamond, that's the N3 center. So you can see the CVD synthetic diamond spectrum at room temperature is just a broad band. Here you see the silicon center at room temperature, and this broad band here is responsible for your blue fluorescence. But with a small spectrometer, not very expensive, you just need a 405 laser and a small spectrometer, you can visualize this really easily. Okay? So this distinguishes them by spectroscopy right away. And here just to show you how that looks like when we go low temperature, before treatment, after treatment. laser, we have a laser beam that goes through this sample, laser beam that goes through this sample. You can see the growth lines nicely. And here you see how it's in this specific sample, how it is structured. So you have yellow and orange PL an interval of those, of the alternating bands of yellow and red. And that's from, again, 467 versus NV center. NV center red, 467 yellow. After treatment, one big broad band. At low temperature, as you can tell here, it gets really complicated with plenty of little wiggles on it. So at room temperature, this would be just a broad band. But this is just to show you how this looks like in detail. Treated natural diamonds, believe it or not, we can work on those by fluorescence as well. Fluorescence gives us some ideas whether a diamond has been treated or not, at least in certain cases. So here are a few examples. The most easy examples for any person, any gemologist, anybody who has a UV lamp, are pinks. Natural pink or not natural pink. Okay, first you need to know, is it a type 2A or not? Well, use cross polarizers, that does it quite easily. If it's type 2A, you can't do it yourself usually. But if it's a type 2A and it fluoresces like that, if it's a type 1B and it fluoresces like that, if it's a type 1A and it fluoresces like this, you know the stone is either treated or synthetic and treated. So you can't tell from this without experience whether a stone is natural or not. But this is actually a natural diamond that has been irradiated and annealed to make it purple. And this is a multi-treated stone. These are multi-treated stones that have been HPHT treated, irradiated and annealed to make them pink to red. So this material is easily identified since a natural pink type 1A material, the argyle material, for example, all fluoresces blue, almost exclusively. I've never seen an argyle that fluoresced anything but blue to maybe slightly greenish blue, but it's generally blue, 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 no matter what excitation you use. So this kind of a response will tell you your stone has been treated. Then if you have a green diamond, that fluoresces like that, you take the spectrum of it of this strange, chalky, blue-green fluorescence, and it'll be a really strong band at 523 nanometers. You can be reasonably certain that your stone has been just simply irradiated without any heat, anything else, because this is an interstitial-related fluorescence that exists only between direct after irradiation until about 100 degrees Celsius. So if it gets more heat than 100 degrees, it's gone. Okay? And sometimes in irradiated stones, you can see surface-related fluorescence. It has been published years back that there is a thing called fluorescence cage, which is actually not correct. That stuff is just an optical artifact. But sometimes you do see surface-related fluorescence like this. That basically tells you how deep your irradiation went. Today, most material is electron irradiated. Electron irradiation, especially when you go at lower energies, doesn't penetrate very deep into your diamond. So you penetrate maybe a millimeter, millimeter and a half in it. And if the stone got some heat during the irradiation, you will have H3 center accumulated inside your color layer. So this stone in immersion actually showed just a nice blue color layer right here. Okay, so that gives you a good idea about treatment. To show you what treatment does to a stone, classical stone, and its fluorescence, there you go, colorless type 1A diamond. After irradiation, went greenish blue, and then we started heating. And you can tell that the color and the fluorescence changes at each step. And at about 650 degrees, it gets dramatic. That's when the vacancies that you introduce by irradiation start to move all around and catch the nitrogen. Then they form NV centers, such as H3 and H4. And those things give you this yellow color and the green fluorescence. And you can tell it all in every step here. Here you got before irradiation. This is straight after irradiation. So that's this fluorescence. And then at 650, you have a really strong H3 center, which is this green fluorescence here. So this is the sequence of a regular type 1A diamond, Cape type, after irradiation and annealing. Now let's make a little quiz in here. Anybody who was at the NAJA conference can't participate. Is this natural or is this synthetic? Any guesses? It's natural. It's a natural diamond. So sometimes you have natural diamonds that show rather dramatic and geometric patterns like this one. It's not very common, but sometimes you see them, and they can be really, really confusing. Let's have a look at another one. This is a vivid yellow diamond. Let's look at... Excuse me?
If you only saw that picture,
Yeah.
would you still have the same conclusion? If so, what are you actually looking for?
Well, here what I'm... Wait, let me go back on this one. There. So what I'm looking for, this one is, first of all, the exact distribution. Then here you have these strong lines that traverse the stone. So it has been plastically deformed as well. You can theoretically make something like that in a synthetic, but it's very unlikely. And then what gives the thing in the end is at what excitation does it look best. In this specific case here, this stone had the strongest features under shortwave UV and much less so under deep UV. For us, that gives us a good indication. It doesn't always work because there are synthetics that behave similarly. But you look at this and you turn the stone around, you turn it in all directions, and you just, with experience, you know that these things are actually natural. Whenever you have a doubt and a stone like that, you just take it out and you take an infrared spectrum, and from there you usually know.
So if you saw this at 220
Yeah.
instead of 250, 254, you would think differently? But because it's
No. It's like, what,
trying to understand the difference between the shortwave and deep wave.
yeah, what you do is you go basically long wave, shorter until you're at deep UV. So we're having 6 excitations, and the sequence of those 6 excitations usually gives us a straight conclusion, natural or synthetic. But the image itself can be really disturbing. I mean, sometimes I show a few more now. Sometimes really it's like you're like, wow, this looks synthetic, but you know, sometimes it takes more than just the fluorescence image. But here, for example, so guess on this one. Natural, synthetic, natural. Another one, yeah. So here what gives it away are actually these features here. You can see these lines here. That's like that gives away that this is just a mixed growth diamond that developed these interesting sectors. So they're a little different than what you see in a synthetic, but this can be really disturbing when you see it. But again, this is just exceptional. These stones, we see a couple of them once in a while, so it's not very common. This one, natural or synthetic. This is indeed a synthetic. So this is a kind of different type of synthetic. So here you have like I'm not sure if this was actually a twin, it's possible. And you see these interesting lines. So synthetics may appear rather different to what you see published everywhere. Those typical sectors sometimes look rather distinct, different. This one? Yeah, this one was actually, this stone, I think we did everything on it because I was like, is this synthetic or is it natural? It's natural. It was a pink rough, it was red. They brought us a red rough and it fluoresced like that. So first of all, we knew immediately it's treated, but then was the question, okay, now, is it synthetic or is it natural? So it had these dramatic growth sectors. I know these growth sectors quite well because during my PhD, I treated quite a lot of type 1b stones, and they do develop growth sectors that are very strong. But this stone was unbelievable. I mean, the growth sectors were so clear, but it turned out to be a natural diamond, but this needed a little more than just fluorescence. This one? Any guess? What was that? That's natural as well, but it's a treated stone. So this is a treated purple, type 1b stone that we treated to make it purple. So here you develop those sectors the sectors are present prior to treatment, obviously, but through the treatment you introduce these strong NV centers and H3 centers. This one? This is natural. So natural diamonds that have been plastically deformed, they develop those lamellae along the octahedral direction, usually not just in one direction, but in several. And this is very characteristic, but it can, in some case, resemble what you see in a CVD diamond. Not always, but sometimes you see things where you're like, man, that looks kind of like a CVD. Then you test the diamond, and it just turns out to be plastically deformed. This one here? Oh, no, I think it's just the image. It's a marquee cut. The what? Oh, this is just from plastic deformation. Yeah, this is just plastically deformed. That's what they always are. This one? If you have Journal of Gemology and you read it, you could have seen it probably. This is a synthetic diamond. And I still don't have an explanation why and what it is, but it turned out to be synthetic via spectroscopy. So this one, by imaging, there was no way to tell. I was like, what is this? I thought it was natural. And then we did all the spectroscopy on it. I go, nope, this is not natural. So it turned out to be synthetic. Looks like dislocation networks, but they're not. So I have no idea until today what they are. Okay, let's have a quick talk about testing of melee diamonds by fluorescence techniques. I'm going to limit myself to yellow diamonds because we don't, yellow and colorless because we don't have time for more. Let's start, why do we need to care about these tiny stones? Okay, we're talking melee, we're not talking about generally a lot of value. Anyways, synthetic diamonds has practically no intrinsic value. We talk about growth and cutting costs and, resale value, none. What is it all about? It's protecting the luxury market. We need to be able to ID everything and guarantee that there is natural diamond only, especially for brands that are in the public eye. It's impossible to have a synthetic in their piece. So if they have a single undisclosed synthetic in a piece of high jewelry and anybody finds it by coincidence and runs over to the New York Times or to whoever, it's going to be a huge scandal right away. So it's extremely important that we are able to identify all the diamonds as natural and not synthetic. And then obviously the prices. Just to give you a perspective, but this is like on single stones, not on melee. On single stones, we're currently at these prices. So a 1 carat FVS2 diamond costs $5,000 a carat. If it's a 1 carat VS2 synthetic, we're at $70 wholesale right now. Okay, a 1 carat stone, $70. These are small quantity wholesale prices, not large quantity. So I don't even know how low they go if you buy their entire inventory, but if you buy a single stone, you can get it at $70. Moissanite, $20, a CZ, maybe $2. So obviously the price difference is what it makes. And in melee, that's especially important when we talk about things like vivid yellows, where we talk about $3,000 a carat anyways, wholesale. So we're talking about goods that are valuable and pricey. Here, you all know the pre-testing machines, pre-screening machines, automatic machines. They always have a certain quantity of rejects. So this is a parcel that has been rejected by automatic testing, has been sent to us. The label on the thing was likely synthetic. We tested them, and that's what we got. So basically, the vast majority was natural, a couple of HPHT synthetics, a synthetic sapphire, 3 CVDs, and 3 naturals that did phosphorus. So in these reject parcels, generally the vast majority of stones are natural. You often find very, very few synthetics in them. How do we do it? Here I'm just going to show you this little video if it works. It should, yeah. This is like when you do it by spectroscopy. So here, this is our instrument, the smaller one. There are diamonds in there, and this is the spectrometer that measures the spectrum. In green, it says it's fine. In red, it will tell you it's not fine. And you hear a little sound. That little sound is it's fine. That sound, it's not fine. Okay, so you stay with your eyes on the microscope and you just work through your stones and it tells you if it's okay or not. That's for colorless goods for, let's say, relatively inexperienced users. For colorless goods with an experienced user on the bigger system, you usually don't need spectroscopy. You do it by imaging only. So this is a CVD diamond. You can see the broad band. This is the N3 center. And the system automatically detects what kind of spectrum it sees. And here you see it in the beam. It's in the laser beam, I think, here, not in the UV beam. Okay, there you go. So, in synthetic diamonds, while colorless diamond is a problem that has reached the entire market and everybody was like panicking about it, we have all these automatic machines all over the place. The biggest problem is actually not colorless, but yellow to orange. In vivid yellows, I have not seen a single parcel without any synthetics in the past 15 years. Not one. Not one parcel. Except like when you get 20, 30 stones from a certain supplier, that might be fine. But as soon as you get a parcel that's whatever, 1,000, 2,000 stones, you always have synthetics. So the worst parcels we ever had was 45% synthetics, but that's like really just like somebody gets a new supplier, sends them over, and I'm like, yeah, you have to forget about that supplier. But generally speaking, it's 1 to maybe 2% of synthetics, but they're always there. And they are very difficult to identify efficiently. So here you see a parcel that we tested. So it's a couple of thousand stones. 8% of the stones turned out to be synthetic and 1 CVD. So these are HPHT synthetics, and here's a little CVD that sits in there. So this is the typical result we have of vivid yellows. And the more vivid they are, the higher a percentage of synthetics. But don't be fooled, we have synthetics even in light yellows. Regular, fancy yellows, etc., you find synthetics in all of them. This project kind of started around 2011 because that's when we had to test. This is the entire stock of a large company that starts with C. You can see in the bottom who it was because it was not secret. We tested their entire stock. At the time, it has been always tested by some other lab, but just in certain percentages and not the whole thing. Here we tested the entire stock, and that's what we found. So we had synthetics in all diameters. The largest percentage was between 1.5 and 2 millimeters. Here we had 4.5% of synthetics. So you see they were everywhere. Now the distribution is kind of different. Today we find more and more in these really small sizes. So we find 0.7 millimeter synthetics, 0.6 millimeter synthetics, things that you wouldn't even think are worthwhile even cutting, but they do. They make them really small. You find them in anything. And then besides synthetics, the one thing that you should all keenly look at are treated colored diamonds. They weren't very popular, very common for a long time. In all the parcels we have seen in the past years, there was from time to time you had a small irradiated diamond that was in it. That was not that hard to identify. And in the past 2 years, we started seeing more and more HPHT treated melees. So you see these vivid yellows here? These are both HPHT treated. Now, how does this fit into the fluorescence topic? Here's the fluorescence of it. So these stones fluoresce differently than what we expect for a vivid yellow. So if I see a vivid yellow of this kind of a color, round brilliant, and it fluoresces like that, blue, I'm like, whoa, something's wrong here. So then from here you have to go, these stones, we can't conclusively identify them by fluorescence, but the fluorescence is like a first step. You pick them out, and then take an infrared, and the infrared alone tells you right away, well, this does not exist in nature. This is this combination of nitrogen aggregates plus single nitrogen does not exist in nature, and then there's other features that tell you that this is HPHT processed. And not every lab positively identified these stones as treated. So we had in Antwerp, we had a rather terrible experience where another lab just said, we had like 40 stones sorted out as HPHT treated. Customer sent it to another lab and they said, all fine. You know, that's the situation we're in. Because this stuff needs a certain expertise to figure it out, especially when you send it in volume. You know, a lab can't do everything on every stone because the testing needs to be economically worthwhile. Just very briefly, brown to pink. Just be aware, brown diamonds, you have synthetics in brown diamonds all the time now. The CVD growers, it's not worthwhile for them to HPHT treat all this small stuff. they grow often, since they grow them fast, they grow them brownish, they just throw them in brownish parcels, and that's how you get them. So you get them in the lighter browns, sometimes in the regular browns, but this is like a typical color here. And it's like average also maybe 1% of stones, 1 to 2% of stones are synthetic in most brown parcels that we're testing recently. And then just short word on the book that this is often referring to. This is a book I just published. I got a couple here, or they're available at the Naja booth. I think it's G11, or G11 in the upper floor here. This is a book that gives you an insight into fluorescence in diamond. It explains various things that I just explained you here, but the vast majority of it is just really pretty images. So this is the best images I've taken in the past 15 years on our fluorescence system of natural diamond and synthetic diamonds and natural treated diamonds. Here's how that looks like on the inside. So you have these spectacular images. This is from several million diamonds that we've tested in the past years. And these are the best images that were recorded over this period of time. And this is just a quick look at the inside. So they're full-page images of fluorescence images of diamonds, with explanation of what you're actually seeing. So it's not just the images. Okay, thank you very much for your attention.
Any questions for Dr. Hainschwang? Yes, go ahead.
Hi. We have some devices that I just want to ask this big question. So, HPHC synthetic diamonds under 222, they highly glow green. In the phosphorescence, they continue to glow. But like 99% of them they are inert under 365. But some of them, they tend to have a little bit of, reaction to 365, which is not for you. I haven't seen it yet.
They do.
So what's the reason? What's that 2% is doing?
What do you mean, the ones that fluoresce on the long wave?
Yeah.
It's basically what it is. It's if you look at the yellow fluorescence in these stones is generally caused by this 484 nanometer defect that I've shown. So you've seen in one spectrum at 484, and then you have other defects. 484 fluoresces green. 484, generally speaking, is only excited at low temperature, but in certain stones, you can see that also at room temperature. And if you see a 484 at room temperature, you will have a greenish glow to it, greenish, yellowish green. That's very likely what it is. I mean, I've seen this myself. I see it all the time. When you have a high-power UV source, long wave, you will see some fluorescence in HPHT synthetics in many of them. Not all of them, but quite a few of them will have a slight yellowish fluorescence to them, yellowish, greenish, yellow fluorescence. So it's not uncommon. I've seen it. And some of them fluoresce red as well, orange-red. I've seen HPHT synthetics that fluoresce orange-red instead of the phosphorescence that you just described, this green-blue. Sometimes they fluoresce orange on the deep UV.
As grown CVDs, they always look inert to me under 365, but some of the CVDs, they again fluoresce under 365. So is it about treatment? Like, maybe?
No, it's I mean, when they're untreated, they're just orange on the long wave as well. But it just, as I said before, we're using this system that has so much UV power that anything fluoresces. That's why I'm saying the vast majority of CVDs, for most UV sources, standard UV sources, they're just going to be inert or very, very faint, a very, very faint glow. So they're not like strongly fluorescent.
That's what I'm asking, like standard 365
Yeah.
low power UV source.
Yeah, they're
CVDs and HPHTs are like, I don't know, 99% inert. But there are some CVDs that I see they glow. Of course, not like a natural diamond.
Yeah, they fluoresce a little. It always depends on the intensity of the fluorescence. So, they're quite variable. So sometimes they're super faint, sometimes they're stronger. That's just variability of fluorescence. You see that in natural as well as in synthetic diamonds. Yeah, yeah, sure.
Questions? Any more? Yes.
Can I ask you to, I think you just touched on it, pull up the slide where you had, all the, at the long way where you had of your synthetics where you have the blue all the way around,
The CVDs?
please.
Let's go back. This one? Yeah.
So when you're showing, and first of all, I'm not a scientist, I'm not a gemologist, I should ask the question differently. Please help. My understanding when you're saying, oh, this is all at one wave, so is this at 365 or not?
Up here, you're in what we consider longer wavelength. So longer wavelength is anywhere between 350 and 400.
And then how much power? So the top left, is that at, that's not at 5 watts, right?
Yeah, this is way more. Yeah, this is with our system, yeah. But you know, it's also, I can't tell you how strong it fluoresces under our system, because in the end you have to take a photo. So you choose an acquisition time with your camera, and you can tone it down to make it fluoresce less bright. So I can't tell you if this one fluoresces strong or just medium. But any of those diamonds, when you look at them under a regular 4 watt, 5 watt UV source, it will be a very, very faint fluorescence at this excitation. So these are not strongly fluorescent stones at all.
So then this is a question, so then to date, you really haven't seen any synthetics that fluoresce, if one is, for the trade as a D1 tear, 365 at 4 or 5 watts. You haven't really seen, is this a question, you haven't really seen any that have fluoresced blue yet? Is that accurate?
Well, I mean, you see stones that do fluoresce blue, but it's going to be really faint. It's just a faint blue fluorescence. I have never seen anything that's like medium or strong. Strong for sure not. Medium, debatable, but I don't think so. Unless you hold your stones this close to your UV source, maybe. But it's generally speaking, they're inert or faint fluorescing blue. So you just, like something like in nature, you're never going to see. And in the CVDs also, when you have if you have something that would fluoresce a bit stronger on the long wave UV, it's just going to be a very homogeneous blue fluorescence. In natural diamond, even with a regular UV, standard long wave UV source, you oftentimes see at least some kind of inhomogeneity. So it's not generally just one blob of homogeneous blue fluorescence. And CVDs on the long wave UV, they always look just flat, like you see here. This top thing, they just look like flat color fluorescence. That also distinguishes them. But it's the faint fluorescence. So the stones that you have to be concerned with are stones that fluoresce not very strongly. Everything that fluoresces strong, you can pass through. Again, I have to limit myself to colorless diamonds. Okay, this doesn't go for colored. In yellow colored diamonds, you can have very bright green fluorescing stones. So.
And then in the beginning of your presentation, you were talking about zim goods. Is that during a particular time period of recovery, like during a particular distribution through that pipe, if you will? Or have you seen it over the course of time?
You mean that?
What time period are you looking at that rough from what recovery period of time?
You mean those mixed growth stones with asteriated diamonds? These ones. I mean, this has been stones for the past 15, 20 years, I guess, that I've seen all over the time. They're always the same, but they also exist from other deposits, by the way. This is not limited to Zimbabwe. Asteriated diamonds have been published way before. There is some in France in a museum that have been published by Rondo some time ago. I think they date from I don't know when. So there is other deposits that produce this material, but Zimbabwe has just like, they have basically blown it out of proportion. Now you see them everywhere, these little plates with the sector growth, but you don't see the phenomenal ones that are one single crystal with a phenomenal pattern. That's rare. The plates are less and less, they're quite common. I mean, you see them quite commonly here. But that material is always like that, yeah. Mm-hmm. Okay? Thank you.